Good afternoon, everyone, and or good evening, depending on what part of the world you are in. I'm Aditya Paranzape, so I'm an associate professor at Monash University. It's late evening for me, so I was about to say good evening. And so, welcome to this second talk as part of Robotics Café. So, as we told you last week, Robotics Café was started with the idea that we create a forum in India where people from the academia, industry, government, and broadly robotics enthusiasts can get together and have an open discussion. That's why it's called a cafe. There is no bar. We talk technical stuff. We like, we just saw, probably some of you who joined earlier saw us just joking about things. That's how it goes. We get together, we talk something nice, and hopefully at the end of it, we learn something interesting, we network, and we have something nice to take away. So that was the spirit behind starting the cafe. Also, as you might know, some of these international conferences, the top conferences in robotics, IROS, ICRA, RSS, while the Indian academia is very well represented at those conferences, the Indian industry and the government very often is not. So we also felt that if we have a forum like this, an open forum where people can talk with sort of no strings attached, let's say, from their professional affiliations, it would help us create a nice platform for everyone to get together and exchange ideas. And in the long run, we hopefully have the equivalent of IROS or ICRA, whatever the top robotics conferences are in India as well. So of course we are open to an audience from around the world, but we are also very mindful of the fact that we have this India-centric mission that we hope to get to. So with that preamble, let me introduce our speaker today. We are delighted to have Professor Arun Kumar Singh. He's a professor of motion planning at the Institute of Technology at the University of Tartu in Estonia. He's the PI of the AKS lab. His research interests lie in developing algorithmic foundations of robotics, especially motion planning, control, and learning for control. So his group consistently publishes in top conferences and journals in robotics. He's currently leading an 8M European project called XSCAVE. I hope I've spelled it correctly, which aims to develop AI-based planners and controllers for safety critical systems involving heavy machinery in forestry, logistics, and construction. So, Arun, a pleasure to have you. So, handing the floor over to you now. And by the way,
Okay,
just as a quick housekeeping announcement, if you have questions, please raise your hands and we'll bring them to Arun's attention. Or you can hold on to if you hold on to your questions at the end, Sandeep here will coordinate the questions for you. So, Arun, over to you. Thank you.
okay, great. Thanks, Aditya, for the introduction, and thanks, Sujeet and Sandeep, for inviting me. Uh, uh, Happy to be here. In fact, I did hear the talk last week also from Professor Ghosh. Um, Actually, I spent 1 year in his lab way back in 2009, so after my undergrad. Um, and he was also my like thesis reviewer for my PhD. Okay, so let's start. Today I would be talking about how do you leverage uncertainty for reliable model-based planning and control. And this essentially the talk will be things that we have done, some things that other people have also done um on this topic, and I would try to give more like intuitions on how things are working on this uncertainty front. So there's basically three components, like how does uncertainty feature in model-based planning. So we'll mostly talk about like what we call as aleatoric uncertainty, and like we'll cover epistemic uncertainty only briefly, and how can we leverage uncertainty estimates for more robust planning. And then how do we learn this uncertainty, like where does uncertainty characterization come from. So these three are the broad components of this talk. So let's start with the basic premise. So let's start with the the basic definition of what is called as a model based, what I call it the model based planning. So imagine that you have a world model um, which can take in action. And suppose you have some policy, some logic for generating those actions. And so if you give this world model, you give this current state and perception, and so world model comes, and what comes out of the world model is the state evolution. So it may not be the state evolution of just the ego, like the robot that you're planning for. It can be for the other agents also, or how for example, the objects that the robot is interacting with changes. That's why. So it's an action condition world model, perception conditions. You give actions, you get out, you get something, you get out state from this world model, and then you evaluate some kind of cost functions on the state, and then you have some logic of how to update my action to minimize this cost. So that's the whole basic template of model-based planning. You can also call it depending on where you want to publish it. Uh, if you want to push this to a NeurIPS ICML, you'll call it model-based RL, and we would try to learn this world model. And if you're trying to publish to CDC, we will call it like optimal control and model predictive control. So, but more or less, they're all referring to kind of similar things. It's just the community differs in how they look into it. So yeah, so you have a world model F that takes an action, gives you some state X. X can be the ego motion, can be the environment. Everything is encoded in X. So what you need is you need to find out some U, which gives you some minimizes some notion of your, which minimizes some kind of function over the state of the control. And this kind of cost can capture some desirability, like how good your state is, how good your action is. So it just, and then basically model-based planning is an optimization problem where you try to come up with this U which minimizes my cost function. Um, so cost can depend on X can depend on U. You want to minimize this. You can do gradient descent on that and come up with the optimal U. Or you can use some other like Newton's method, whatever. You can come up with different algorithm to solve this problem. Good. For example, let's take this example. Autonomous driving. A world model can, for example, be something that consists of vehicle dynamics and trajectory forecaster. So vehicle dynamics would be our own ego vehicle. How does the ego vehicle change? And the trajectory forecaster can be something that how the neighboring vehicles would react to your motion and how the neighboring vehicles would move, and those can be affected by the ego motion itself. For example, let's consider a simple traffic setting where, and depending on how the this would be that forecaster would tell how the obstacles would move, and and the ego would move something like this if you give some action. So in the case of autonomous driving, this would can be one way of doing this world model thing. So you has two components: vehicle dynamics and trajectory forecaster. And so X would contain the ego vehicle and neighboring vehicle trajectories. So one critical component of your cost is the collision risk. Like what you want to care about is you want to minimize my chances of colliding. So you don't want to collide and risks injury. So we want to compute action sequence which minimizes collision risk or ideally drives it to zero. Um, so one more running example that I will do in this talk is of monocular vision-based navigation. So imagine that there is a robot here, and it sees this robot front view. Okay, and it has some kind of a action sequence which leads to a trajectory. So we want to um, infer whether this trajectory is going to collide or not, based on just the image, not depth. So there is no depth information. If there's depth information, then it's mostly a trivial problem. So just with the image, can we do that? So what I call is a monocular vision-based navigation. So here you can think of your world model as like vehicle dynamics plus something like a clearance predictor. Example, it takes a trajectory and predicts how far you are going to be from the obstacle, and it is conditioned on the perception, which in this case is the image. And what you get out of this is the state, which consists of the x where the robot is, plus also, let's say, the clearance, some kind of estimate of the clearance, this one. So the whole model can tell you how the vehicle is going to move, the vehicle dynamics part, and plus what kind of clearance you can expect based on the image that you're seeing at this moment. Again, we will try to see whether we can minimize risk in this kind of setting by including that in the cost function. So these two are the basic settings that I'll be considering. So the one critical question is whether you want to do your world model, or the model of how the system evolves. Should it be deterministic, or should it be stochastic? For example, let's say we have a deterministic forecaster, so it tells that the vehicle, neighboring obstacle will move like this. Or we have a stochastic forecaster, which doesn't tell how the obstacle is going to move. It gives you different possibilities. So it gives you this kind of multiple trajectories that the obstacle can take. And so in this case, the forecaster can be a deterministic prediction for the neighboring vehicle trajectory. We call it tau, let's say, in the slide. So in this case, the planning problem is very simple. In the deterministic, it's a simple optimization problem. We can use gradient descent. But the problem with deterministic forecaster is that it does not capture uncertainty, because it's very difficult to predict what the neighboring vehicle would do. Its intent is unobserved, so you don't know what its intentions are, whether it wants to cut into your lane or continue moving forward or want to accelerate or deaccelerate. You can take the past history and make some guess. So it will be very difficult to compress this guess into one deterministic projection. For example, you can give the most likely trajectory as a deterministic prediction. That is one possibility. Or you can give several different predictions. And if you're giving just one prediction, planning problem is easy. But if you give multiple predictions, then your planning problem becomes very difficult. So the planning problem captures but the setting is more like sophisticated, because it captures the inherent uncertainty in this setting, because actually in reality you don't know how the other guy is going to behave. But in this case, when you have stochastic forecasters, you have a more complicated planning problem. But so you get more info, you are doing more sophisticated reasoning, but that process is more complicated. So similarly, in the case of this vision-based navigation, there is a very intuitive motivation to think of it as your world model or your prediction mechanism to be stochastic rather than deterministic. So a deterministic setting, let's say you have a model which predicts that if I take a particular sequence of actions, this is going to be my clearance, this black, this is going to be my clearance from the obstacle. But since we are conditioning this just on the image, so essentially we don't know the depth. So there is an inherent uncertainty in the depth. So it makes sense to somehow capture this uncertainty and not give one estimate of how the obstacle clearance will be, but give you like a bunch of predictions. And those predictions would be some kind of like samples of some random variable. So here in this case, it makes sense to take out your model, to introduce uncertainty into your model, or rather model make your model stochastic rather than deterministic, because then it can capture the inherent uncertainty in the problem, although now you are doing more complicated optimization. So let's take this example that so let's assume that we are convinced that we have to take this kind of stochastic approach, that our world model prediction should be not deterministic but stochastic. So instead of predicting one, we'll predict like multiple ego vehicles trajectories. So now the key question is how do you leverage these predictions? for improving your planning. So let's take some like a notation. So imagine that we have an x of e, which is the ego trajectory, and let's say tau is my obstacle trajectory, and tau is a random variable because we don't know what the obstacle trajectory is going to be, and we can define like a per step collision constraint, and we can define a worst case collision constraint by just taking a max of per step, and then you can then you can define what we call as the probability of uh, what do you call it, chance constraint, or the constraint that whether you're going to collide or not, as the probability that f of x, e, and tau, your collision constraint gets satisfied, should be greater than some threshold eta. So this kind of constraints are typically called the chance constraints in the literature. So it's a constraint over some over a probability space. So f, since tau is a random variable, so f also will become random variable because it has this tau as its argument. So depending on what tau takes, f can take that value. So the probability that f is always less than equal to 0 should be greater than some eta. So alternately, you can also define collision risk as just the right hand side, like what is my probability that I'm going to collide. So what you would want to do is you want to, so a typical planning problem consists of minimizing my collision risk, and there could be some other costs like smoothness, control cost, and tracking cost. It can be, so there can be some other costs, but the main thing that I'm focusing on is the risks, like how do you minimize this collision risk given that tau is a random variable. So the core challenge in this kind of this uncertainty driven planning is how do you compute this right hand side, left hand side here, right hand side here, how do you compute this probability? So how do you compute probability of f, x, c, comma tau? So this is the main challenge, because if you have this, then you can figure out some way of minimizing these functions. There are some like ways to sophisticated optimization algorithm. Um, so the main challenge, like if so I'll give one like a special case. So if tau is Gaussian and f is like affine, then this term is pretty easy to compute. So then you can have a closed form analytical expression of the probability based on you can relate CDF to the probability, and then it becomes easy to figure out what this number would be for a given tau, for a given distribution of tau. So tau is Gaussian, f is affine, then this is pretty easy. But in general, things are a little more complicated. So um, because typically in like autonomous driving, you have this trajectory forecasters. So these are not like the SOTA methods are not rule based. These are some kind of a very large neural networks with multi-area attention transformers. So they do. So your probability distribution here tau, the P of tau, which it belongs to. So this can be very arbitrarily complex. You may not be able to characterize that because the way you model this is through some kind of a neural network. For example, there is this famous trajectory predictor, which is extensively used, called Trajectron plus plus, which uses conditional variational autoencoders to uh, predict multiple multimodal trajectories. So so the probability distribution is very complex because we model this through some kind of, you model your prediction through some very complex neural network. So in that case, there is no exact formula for this. So there is absolutely there is no hope that you can write this in some kind of a closed form solution, closed form symbolic formula. So what we need to do is to estimate through obstacle trajectory sample. So the assumption is that like I don't know what P of tau is, but I can sample from this tau. That is pretty easy. You can query multiple samples from your neural network. So you can query this kind of samples. So you have two, three, or like you have 5 samples you can query. So we need to estimate this collision risk or the probability whether you're going to collide by just through these samples. And that's one of the main uh, essentially what the problem reduces to. So I give you different possibilities that the vehicle can move, and you estimate what's the collision risk. Now, it will be very tempting to uh, just, let's say we draw 5 samples and we just evaluate whether all those 5 samples are going to collide with this, uh, let's say the green ego, and if none of them are colliding, we claim success, we claim that the scene is safe. That's very tempting to do, uh, and actually that is one a baseline method, which is what's called the scenario approach, which actually does that. But that's one. But typically, it will for that those kind of methods to work, you would need not 5, but maybe like 5,000 samples. So just doing it with a handful of samples, predicting collision rate, that it's has a lot of complexity. It's not so straightforward. So basically, there's I'll- there are several works which does find some kind of approximate way of computing this sample risk through samples, and I'll give you the basic intuition of how all of them works. So let's say we have an ego trajectory. We draw this tau of j, which is like the trajectory samples from the probability distribution of my trajectory forecaster, which characterizes v of tau. So I have a neural network forecaster. I don't know what distribution it characterizes, but I'll draw some j number of n number of samples, and j be the index, like I have j trajectory sample that I draw. So we can define my violation of my collision constraint as some kind of max operator. So it is 0 if this f is satisfied, if f is less than 0, otherwise you pay a price f. Very simple, this what do you call it, the penalty, collision penalty. And
Yeah, yeah, yeah. So, uh,
hello, is there, was there a question, was there a question, or hello?
I think not. Let's
no,
move
no,
on.
no, no, nothing.
uh, okay, should I continue?
Yeah, yeah, yeah. Sure, sure.
Yeah,
Okay,
Yeah.
yeah,
okay,
please.
okay. Yeah, so we can, so based on this ith obstacle trajectory, we can compute how what is my collision violation. We can give some numbers to it by just computing this max penalty, or what is called the collision residual, or this constraint penalty, let's say. And so for jth trajectory, this is my constraint penalty. Now, so if you draw like 10 samples or 100 samples of obstacle trajectory, you can compute 100 different f bar of j corresponding to each obstacle trajectory. Now, uh, all the risk estimators will do some kind of statistics over this to estimate the risk. Okay, so basically, if you just average it, then what you got is, then you get something called a sample average approximation. If you compute conditional value at risk over that, so you get CVAR approximation. And there was this the recent method that we had, and taste, what is called as estimation based on maximum mean discrepancy, which you call as MMD risk. So that will give you another kind of estimation. So different statistics computed over this will give you different results, which with their own complexity. For example, it might be easy to compute, but it may not be sample efficient. I'll come to exact definition what sample efficient mean in this case. Or it might be sample efficient, but very difficult to compute if we need to do more numerical operations over that. But nonetheless, like essentially the idea is you compute per sample violation of your constraint, of your safety constraint, and then do compute some statistics over it, and that will give rise to some kind of your risk estimation. So as I said, so sample average is just take the average. That's it. Or rather, like some kind of a, so not exactly average. So you have to define some indicator function where if this is 0, then it is 1, and so if it is yeah, if it is satisfied, it's 1. It's not satisfied, it's 0. But more or less like that. So you compute the average over this, then what you get is called a sample average approximation. Very straightforward, but works really well. It's like pretty old paper, online, but is a pretty strong baseline. So if you want to compute risk, so it works for and it works for any arbitrary constraint. So you have a constraint which depends on some random variable, and you don't know what random variable distribution is, but you can draw samples of it. So just evaluate your constraint over all of those samples, and just compute the violation average over all of them, and that is your risk estimate. And it will so as you increase the number of sample, it will asymptotically converge to the true risk. Now there is another thing which is like the kind of SOTA risk estimator, which is based on conditional value at risk. So you compute the alpha, like the quartile value of, so you get all those f bar j samples, and then you compute the alpha quartile of that, and there's a few more steps on that, but and then that will be your CVAR estimate, and that gives you another estimation of your risk. Again, it will have its own tendency, like depending on the n, it will have its own convergence rate. So these are two popular choices for the risk estimation. The good thing is it works arbitrary. Just 1 second. It works for any arbitrary distribution, any arbitrary constraints. So you can actually apply it to any problem. And there was this recent method of ours called the MMD risk, or MMD-based risk, where the idea was that we should formulate this risk estimation as some kind of distribution matching problem. So if you so this, we want this f to be so this f bar of max of 0 comma f. So since tau is a random variable, this whole thing also will be a random variable. Let's call it PFF bar. Now I don't know what my PFF bar is. It's very complex because tau is very complex, but I know that it will always look like this. It will always be on the right hand side because this is always positive. So this will be the distribution. Now if this distribution collapses to a Dirac delta distribution, then I'm safe, because then all the violation samples have been converged to a Dirac delta distribution. So I have two distributions. I want to modify my control samples in a way that the two distribution becomes similar, and that's what the intuition was. And to match two distributions, there are many different techniques, but MMD is one like popular one and has some advantages. So that's what the intuition was of our work. So this is another way of estimating risk. Again, you take the violation samples and do some estimation over that, and that gives us our risk estimate. And there were like few advantages of this way of doing. And yes, so this distribution matching can be done through several ways. Like you can do KL divergence is one way. Like you can do difference of two distribution by computing the KL divergence of that. But the trick is that the KL divergence needs parametric form of distribution. If you just have samples, it doesn't work. So MMD is one way of computing difference of two distribution based on just samples, and it is essentially some kind of kernelized learning approach. And so the theory is a little involved, but the intuition is pretty straightforward like this. Like somehow you need to make your violation distribution collapse to a Dirac delta. And the way you do is to compute the kernelized embedding of this distribution and the Dirac delta, and just make both of them same. So yeah, and so it worked pretty well and gave us a really like a good sample efficiency. So I'll come to this slide a little bit later. So I say that like so I've said this say this word a couple of times, what sample efficiency means. So like depending on the problem, sample efficiency can mean different things. For example, when you do reinforcement learning, typically sample efficiency means like how many times you need to query the simulator. In case of, let's say, supervised learning, how many data set, how big data set you need. So in this case, what does actually sample efficiency mean? So imagine that when we're computing the risk, we are computing the risk through n different samples of tau. So we don't have the full set. We can draw as many samples as we can. So we have access to n samples. So if you go back to this, like the first figure, suppose I have 5 samples and I compute my risk estimate based on these 5 samples. Now, when the vehicle is moving at the inference time, the vehicle can move along a different trajectory, which may be from the same distribution, but could be a different sample. So if we just formulate risk with just 5 sample, will it generalize to the unseen case? That's what risk estimation means here. And obviously, if your n is very large, like suppose you draw 10,000 samples, then you're more or less covered in the entire space and you're likely to be safe. But but if you're doing at a very low sample regime, like if you're doing this state risk estimation with just 5 or 10 samples, then whether your 10 sample estimate of risk actually generalizes to the full space, like whether you are actually safe. So that what risk estimation means in this case. Sorry, what sample efficiency means in this case? Like how big a n do you need to be reliable in your risk estimate? And there is a like practical significance, like you just cannot arbitrarily make n large. For example, in this autonomous driving setting, if you take n, if you take more trajectories of the neighboring vehicles, then you have to do that many number of collision checks, and those can be computationally heavy. So there is a strong motivation to make n as small as possible. So in that sense, the what MMT was like really sample. We show that it is more sample efficient than the CVAR and SAA, and the main trick of this work was that you can draw a large number of samples, but you don't have to do collision checks or your uh, this collision check over all the large number of samples. You can carefully select a subset of the samples. And so suppose you draw 10 samples, or suppose you draw 100 samples, but don't compute the collision checks or the safety violation across all of them, which can be computationally heavy. So we gave us some like a nice intuition of how to select a subset of that to estimate risk. Like you can only choose 10 out of those 100. And how do you distill the information of all those 100 samples into those 10 subset? So that was the key idea, like our main idea and result of the paper. So yeah, please check out this work. This is very recently published, and we're going to present this in ICRA also next month. So okay, so I just put one simple result, like to show that like if you what happens if you do deterministic prediction versus stochastic. So if you have deterministic, then you can draw, let's say you take one sample out of the distribution, and there's a huge variance because every time you draw, you get a different number, you get a different trajectory. And so you get a very high collision rate with high variance. But if you do the stochastic one, especially with our MMT based collision ratio, you have a low collision rate. We got similar results in our vision-based navigation, and I will show you some videos of this, like after the presentation. So when we had deterministic, when we modeled our vision-based obstacle clearance prediction as a deterministic model, deterministic neural network, we had like 41.5% collision rate. And if when we made it actually stochastic, so we actually made it uncertain and tried to capture that uncertainty and then try to leverage that uncertainty in the downstream planning, then our collision rate reduced from 41.5 to 6%. And this was published in this Robotics and Automation Letters, which again we'll be presenting in ICRA next month. Okay, so till now we have discussed that there is, so it is good to have like if there is the problem setting is intuitively uncertain, then it's very useful to incorporate that uncertainty, and there are several methods to how do you leverage that uncertainty into your downstream planning, okay, to make it more robust. But there is also a crucial question, like how do you characterize this uncertainty? And I'll give you, it's actually a pretty complicated problem, which is somehow often neglected in robotics literature, but we have been facing this problem more and more nowadays. Just imagine that, let's take this example of this trajectory forecasting. So let's say we have a forecaster which predicts something like this. Your red is the ground truth, let's say, and all our predictions are very close to it. Now, is this forecaster actually good? So because if you actually compute the standard metrics of like what you call it, the AD/FD metrics, which essentially measures how accurate your predictions are related to ground truth, then this forecaster will get a very good number. This will be probably the SOTA in leaderboards. But is this forecaster actually good for downstream planning? So what you've seen is that this AD/FD so metrics may be kind of misleading and may not be suitable for downstream planning actually. Um, so the predictors or the forecasters with good AD/FD may not be the best for for your downstream planning. It may make your vehicle more overconfident and risk taking. And I'll give you one small like a mathematical insight like why this happens. So imagine that we built a very simple forecaster. So we have a, let's say, an Gaussian MLP, a simple multi-layer perceptron which takes in map and past history, and it predicts the mean and covariance of my predicted trajectories. So all these black trajectories that you see, I predict the mean and my covariance. So typically how you train this kind of networks is through this what you call it the negative log likelihood loss, NLL loss. And so this is NLL loss. We and then you backpropagate and then you train this your network to do this kind of prediction. And so in this setting, your strong supervision is only on the mean, because that is what you have ground truth for, the tau GT here. You don't have any like strong supervision on the covariance. So your covariance can actually grow and make you underconfident, or your covariance can shrink and artificially make you overconfident. So there is a very weak supervision on this, and because there is no actually you don't have any ground truth for the covariance. And when you learn dynamics also from data, typically you people follow this kind of approach. They have this Gaussian dynamics, and they try to predict mean and covariance. And again, the supervision is on the mean because that's what you have recorded data for. There's no ground truth uncertainty. So with this kind of NLL loss, you have a like you're basically rolling the dice. Sometimes you'll become overconfident, sometimes you'll become underconfident. And typically, what you've seen is that it typically gives overconfident output in the sense that the uncertainty will completely collapse, and then will become something like this. You will get good numbers. Your loss will be pretty low, but it may not be reflective of what the real world situation is. Okay, so that's one of the key problems of this uncertainty quantification. So how do you solve this situation? And by the way, this is not the problem of just Gaussian MLP or just toy setting, but even if you train forecasters using like flow matching or diffusion models, it will be the same problem because your supervision is only on the recorded data, which is like the mean, and not on the uncertainty. So how do you solve this? So one, like let's say, or this Gaussian MLP example. So the intuition is that your uncertainty should be characterized by your downstream task. No, because there is no other way to characterize this. There is no ground truth for that. So what I mean is that, so let's say we have a forecaster which gives me mean and covariance, and I have a negative log likelihood head to train my mean and covariance prediction. We can pass this prediction directly to what we call as a planner, because you want to use this for planning, downstream planning. So if you use this for planning and you get something out of that, some optimal solution, and then you can compute this optimal solution with some ground truth solution, or you can have some additional loss. So during training time itself, the idea is that you take the prediction and pass it through the planner, and then see how the planner output looks and how does it compare, let's say, with ground truth or some kind of other loss function. So the supervision for this uncertainty covariance comes from this planning loop. So here, basically, you would have two heads, the NLL head and this MSE loss head for the ground truth, and then you have to backpropagate through this. Now you have to backpropagate through this planner loop, which is typically an optimization problem. So it makes the problem little more complicated because you have to backpropagate to an optimization layer. So there are things like implicit differentiation or differential optimization layers, which needs to be invoked here. And but that's what the we hypothesize that right way of doing it is. Like we have to backpropagate. The only way to characterize uncertainty, or not the only way, maybe a one good way of characterizing uncertainty is to just evaluate during training time how it affects your downstream decision making. Because a good uncertainty is which kind of helps your downstream decision making. Uh, and if you don't have that, then it'll just converge to whatever value it feels like. And most likely it'll cheat, like it'll just converge to a number which minimizes this loss. So right variance is one that results in control close to the ground truth, or you can have something else also, some
Arun,
other loss.
just wanted to give a heads up, like
Yeah,
if you can wrap up in 5 to 8 minutes, that would be great, so that we'll have some time
yeah,
for questions. Yeah,
yeah. This is the like I think I'm the last two slides.
that's okay. Yeah, I just wanted to give a heads up.
Yeah,
Thanks.
no. Okay, so this end-to-end training is tricky because it differentiates through this optimization layer. And this is one example from NVIDIA's diff stack paper, where they actually used this technique and showed that this actually makes sense, where you do this kind of end-to-end training or task-aware training of uncertainty. So where you the it kind of gets rid of the spurious predictions. So your forecaster becomes more concentrated on towards these regions, which is the more correct region, and there is not enough weightage applied to the predictions which say that it'll just the vehicle will just go off the uh, will just go in every other direction. So it kind of acts as a regularization for the uncertainty of the forecaster, which we also hypothesize will happen through this kind of end-to-end training. And there's one validation of this that actually it works. Um, we actually use the same trick for our vision-based navigation paper. So where we had this, where we did this typical NLL loss-based training for predicting clearance, we had 28% collision rate, but our task-aware model had like 6.6% collision rate. Yeah, so yeah, this is the last slide. So all of this works with basically mostly on electronic uncertainty. So we're also doing a lot of work on epistemic uncertainty, basically uncertainty due to missing data. So one application, we're doing it on off-road navigation. So there's a vehicle which sees the terrain, but only sees part of the terrain. Okay, so it doesn't see all parts of the terrain. So how do you make sure that it only plans path towards the regions which is observable? So we model this as an epistemic uncertainty, and using those uncertainty measures, we are able to bias this magenta path towards this kind of regions where there is the vehicle can be stable, plus it is also observed. Okay, so yeah, that brings me to the end. Incorporating uncertainty in model-based planning is crucial because that gives you some kind of what do you say, make you risk averse. But uncertainty aware planning is more complex when the forecasters is like a neural networks and arbitrary complexity. Plus, there is also care that you need to maintain, like how do you model this uncertainty? Because it's if you just go by the default approach, then your uncertainty may not be reflective of your real world problems. It may be underconfident or overconfident, and it need not, and you have no control essentially over that. Basically, you roll the dice of a neural network, which local optimize converges to will give you some kind of model. It may look good on some metrics like ADFD, but the uncertainty part can be pretty much a gamble. Okay, that's about it. So yes, so most of the work is done by my student Basant, who's graduating in like a couple of months. And these are the funding agencies that based on which all these works have been done. Yes, I'm available for questions. If you want this time, I'll just show this vision-based navigation works. So I'll show some cool stuff. So this is on the drone. So just with the front-facing monocular camera, limited field of view, we do this kind of navigation. We can do pretty actually very complicated collision avoidance just with the camera input. Um, I think the next slide has more complex environment. Yeah, this one. So here, see, so basically we formulated this as some kind of an uncertainty we are planning, and we compared this to some end-to-end approaches and showed that our approach, which has explicitly models uncertainty, gives better results. Um, we have some drones video also. Yeah, this one. Okay, so I guess that's it from me, and I'll be happy to take questions.
Thanks, Professor Arun. Yeah, so we are open for questions. If you have any questions, please unmute yourself and you can go ahead with the question. If you are not able to use your microphone, you can put your question in the chat box and we can read it for you. Any questions? Please raise your hand or unmute your mic and go ahead. Okay, to begin with, maybe I can start with first question.
Yeah.
So basically with monocular perception itself, right? Like you kind of, you mentioned about both epistemic and aleatoric uncertainties coming from basically less data that you see and also from errors from your perception sensors itself, right? So how do you like, is there a good way of balancing these, or do we even have to think about balancing these, or should the model know about these different uncertainties, or you just model it as a
I mean,
noisy measurement, or I don't know. Yeah.
I mean, the technique for both of them is different, but
Yes.
the downstream planner may not care about that so much. Like the you typically use something like a Gaussian MLP or some kind of flow matching or diffusion that'll give you the aleatoric uncertainty. Epistemic would be like you just train the model from several different initializations that'll give you different local optima and with dataset shuffling, and then you get multiple predictions. So each you have several different stochastic predictors, and that captures the epistemic. But when you put it to the planner, it may actually end up affecting in the same way. So, and in many cases, it's very difficult to differentiate also
Distinguish
rhetoric and
between them.
epistemic. Yeah, and in my opinion, it's in many cases it's not even necessary, because the downstream planner. So in the math, there is nothing to say that so uncertainty is uncertainty. The distribution is different. Maybe but anyway, we don't know the distribution. We have to play with the samples. So the downstream math doesn't care about which one is which. It will capture anything and everything from whatever sample level information that it gets.
So at the planner level, you will say there's no need of distinguishing between them.
I would say yes. The samples, so if your risk estimation is sophisticated enough, it will capture those kind of behaviors through the sample information itself.
Okay. Is there any way of like showing this in your validation results, or like how do you actually show this in your work, like in your validation or even in your testing? Yeah.
So so at least in this case, for this monocular perception, we mostly focus on the aleatoric because the epistemic part was not that large. The aleatoric was this, that because you don't have a depth. So for a given image, there can be several depths. So there is absolutely like it can be a noisy situation. But typically, what my hunch is, the way you'd show is that maybe you'd like show the for example, you can take the epistemic uncertainty and aleatoric and put it into your downstream planner, and then you can generate similar uncertainty from a different model, and your planner would behave in the same way. Like so basically the uncertainty source does not matter. We can show it like that, whether So then the planner performs in a different same way. Then that's about it. Like you don't care where this uncertainty is coming from, as long
Yeah.
as we are able to get a good estimate of that.
Okay. Okay. Sure. Uh, okay. Any questions from others?
If I can ask a quick question, Arun. So, I mean, first excuse me if I missed something here, but I mean, you were telling Sandeep right now that there is some sort of a separation between the planner and the uncertainty estimator.
Hmm.
So, is the assumption that the planner does not affect the uncertainty at all?
Uh,
Because one would
yeah.
assume that depending on the quality of your planner, the uncertainty propagation would be substantially affected.
So in so in some cases, like for example here, let's take this monocular perception example.
Hmm.
So the depth information does not depend on where am I. Like your so if you have an image, you're equally clueless about the depth whether you're here or somewhere else.
That's
Because
you're
so
right,
so
but
yeah.
yeah,
So
but if you take multiple images
mhm.
and you have a way of recording an image, then
uh,
wouldn't your selection of the
yes,
path?
yes. So that ties into the epistemic uncertainty, where people actually do this kind of what you call as the active um, what do you call it, the active vision or active perception, where they go to places where
Yeah,
they
exactly.
reduce their uncertainty.
Yep,
So
yep.
yeah. I was not talking about that. And so that is like you also take decisions to improve your uncertainty, like uncertainty measure,
Yeah.
but that only can be done through for the mostly for the epistemic part. Aleatoric part is like the part which irreducible, so you cannot
Oh.
reduce by gathering more data. For example, the lack of depth, or for example, if your sensor has some noise. So there is an irreducible part that you cannot compensate from data. That would be the aleatoric part. So there, no matter where you go, it will be part of your problem. But the epistemic part, and now
Hmm.
this depends on how you formulate the problem. People can say that your depth perception can improve depending on how you move, because your back end slam can change based on how you move, and then your so these are all decoupled. So yeah, in that case, yes, you where you move can affect your uncertainty, and maybe it affects both epistemic and aleatoric, because the problem is formulated in this way. But in this case, we are trying to do reasoning over just one frame. Like we just have one
Okay.
image. So we just have one image, and we want to predict whether if I take this sequence of action, whether I'm going to collide or not. We have a follow-up paper which does this history, which does take into account what you're saying, remembers like where the past measurements were.
Hmm.
But in this particular case, it was just like one single image. And what can you do with that? So that was the problem statement.
Okay. And then, so with your methods, are you able to obtain like a bound, maybe a lower bound on the amount of past data that you need to preserve?
Not on the past data, but
I
not
mean,
in
here it
terms
could be
of.
past frames, but
I mean, we have bounds in terms of like how much samples you need from your predictive model to draw to
okay.
estimate risk. So we have some bounds on that, like how, I mean, bounds in the sense that how fast that bound will converge to,
Hmm.
let's say, very close to being zero. Those kind of bounds are there, but uh, not in terms of like how so we're not translated it to exactly this problem, that how many pass frames we need to get reliable monocular estimate, where because that goes into this fusion and other things. What you want to show here is that without doing that itself, you can do several, like a lot, if you just assume that there is an uncertainty in the system and try to leverage that uncertainty for better decision making.
Okay. Okay. All right. All right. Thanks. Okay, Sandeep, thanks. Over to you
Any
again.
Arun, also like just a quick clarification. So you don't have the map in this problem, right? You don't know the
No,
map
no, no,
to
no,
start with.
no. So we don't have the map. Like we don't know where the obstacles are, just based on like seeing like what is the current image that you see.
Okay. Okay. Sure.
So, Arun, one question: Does the okay? So, does the visual effects have any issues? Like, for instance, is a low resolution camera or anything like that, or the
Yeah, I mean,
lighting effect?
we didn't check for resolution, but we did check for lighting effect, and it has an effect. So you can see here that this is on two different conditions. So this is the green is what we call it the estimated depth. So we take the image, and we can estimate the depth out of that. This goes into monocular depth estimation. So based on the lighting condition, this distribution of the estimated depth changes quite a bit. So the lighting affects a lot, but somehow our model was able to capture the, like bypass, like counter for that. And again, I think that it boils down to the fact that we had this uncertainty model. So when we feed this noise or compared to this noise, this image compared to this image, my variance would change, and that would affect my downstream planner. It should be able to capture that. And actually, it worked for in change lighting conditions like zero shot. We didn't have to retrain the model for. Uh, mm,
Okay.
wait, yeah, this one. And see here, so almost. So it was able to work in like zero light, almost like we couldn't make it more darker than this.
Nice.
But it was trained on like lighted images, like it had like my lighting conditions, proper lighting conditions. Yeah.
So, how much time does it take for training,
Uh,
or any statistics on that?
this one maybe like we actually didn't train on so much of data, and it kind of worked with whatever data we had. So we trained for 3 hours. The amount of data that we had, I think the training ran for 3 hours, 2.5 to 3 hours of this on 5090.
So
Okay.
what was it tried as for generalization? Like, did you try like changing the scene
Yeah,
or
yeah, yeah.
different kind
So
of pictures or
yeah, so we collected like the some data on some scenes, and then we changed the scene completely, or changed the lighting conditions that you saw, and those were it kind of worked for those. We trained only for this ground robot, and somehow at zero shot it worked for the my parrot also.
Okay.
Where did it
Cool.
Cool.
Okay.
Okay.
So I think we are also on time. I think Yogesh
Oh.
had some announcements to make before. I would like to thank Professor Arun for his talk. That's all. Thank you. And then I think Yogesh had some announcements to make. Oh,
Yeah.
there's a
So
question now
yeah. That's,
from Mohammed asking, like, does it work in an outdoor setting?
Yeah. So outdoor is outdoor in the sense like outdoor in the sense that it will work if I just take it outdoors on flat terrain, it'll avoid obstacles. But the we have to, but we are trying to see whether it like on uneven terrains what it does, because there the obstacle and non-obstacle distinction might be little
Yeah.
ambiguous there. So we're trying to extend more to that setting, because we took these things to just outside the building and put some boxes there. It works like that easily.
Okay.
We actually took the drone also outside, so it could fly in outdoor conditions also. But the ground robot, like you have to see it to actually make it like fully. How does it navigate on uneven terrains? That will be the next challenge.
Nice.
Let's thank Professor Arun once again. And thank you
Yeah.
very much for taking time. And this was a great talk. And Yogesh, you
Thanks,
want
Arun.
to just do a quick announcement on
yeah,
logistics?
sure. Thank you, Professor. So the announcement is regarding the If somebody has missed the past session, we have made a YouTube channel and then we have uploaded the past sessions recording. We will do the same for this one also. So please go ahead and check and let your peers also know if they have missed this session.
Thank you very much. Thanks for joining, everyone.
Okay, thank you.
Thanks for inviting.
Thanks, Arun.